Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. Special welcome to anyone joining us from the LAE. We are live on the boostrevision.com website and also streaming live on YouTube. In today's session, we're going to be looking at some practical chemistry. We're going to be looking at the continuous method for monitoring the rate of a reaction. In this session, we'll look at the practicalities of doing such an experiment, including choosing the appropriate equipment and also looking at the sort of data that we would get from the experiment, what we learn about the reaction rate of a particular reaction. As usual, I will be stopping at various intervals to look at any questions that you may have on what we've discussed so far. Feel free to use the chat box in YouTube or in Zoom to post questions to us. And then towards the end of the lesson, we will be looking at an actual exam question and looking at or getting a flavor of the type of question that the examiner would want you to be thinking about. If there are any questions, please do use the chat box. I think I may have mentioned that already. Before we get going, I will spend a few seconds connecting my tablet, and then we'll be all good to go. So do give me a few seconds while I do that. Okay, so it looks like we're all set. So yes, we're looking at rates of reaction and we're looking at the continuous monitoring method for... Okay, so it looks like we're all set. So yes, we're looking at rates of reaction and looking at the continuous monitoring method for... Okay, so it looks like we're all... Apologies for the echoing there, so I had another sort of window open. But right, we're all set to go. And yes, the continuous monitoring method for monitoring the rate of a reaction. So what does this involve? I think a good place to start is to define what the rate of a reaction is. And of course, the rate of a reaction is a change in concentration of either a reactant or a product over time. So you need to have an ability to measure the depletion or using up of a reactant, or be able to measure the production of a new substance, or the making of a product over time. Okay, so typically we would be looking at the concentration of reactant or product, but there are other proxies for concentration. So for instance, you could measure the volume of a gas being produced if in your reaction there is a change in the number of moles of gas from reactants to products. So there are a number of ways of doing this. You could also, for instance, if you're using a colorimetric method, monitor the change in color or the change in absorbance of a specific wavelength of light, which would indicate either a reactant being used up or a new product being formed. Okay, so to emphasize this point, let's highlight the key parts of the definition. It is a change in concentration. That is very important, that in any definition of rates, you're mentioning the change in concentration of a reactant or product. So it could be of a reactant, it could be of a product, over time. So change in concentration divided by time. So all these are important in our definition. And on the screen, you should be able to see two different graphs. One of, well, the first one on the left is of the change in concentration of reactant A as it gets converted to product B. And you can see there that this curve shows the depletion of A, and it gets to a point where you've got no, or it will eventually sort of tend towards the x-axis, and all of your A would have been used up. And of course, if you're monitoring the rate of the reaction by looking at the product being formed, then you would be starting off with zero concentration of product B. So if we're looking at B as the green this time, we're looking at starting with zero of B and making B, and over time making the maximum amount of B possible given the molar quantities of our reactant. Okay, so two ways of looking at the rate of a reaction, either by measuring how much reactant is being used up over time, or looking at product being formed over time. Okay, so another thing to point out is the rate at any time over the course of the reaction. And that, of course, is given by the gradient of the curve at that particular time. So you want to, if for instance, you want to measure the rate at some time x, and I'm going to use time x for the formation of B, then you would want to draw a tangent to the curve at time x. So we're looking at this point here, and we would want to draw a tangent to that point. Let's see if I can get this perfect, almost perfect. So we would then measure the gradient of that tangent, so the difference in y over the difference in x for measuring the gradient. Okay, so that's something we will look at in a bit more detail. So another key point to bear in mind is that the rate at any point in time can be obtained by calculating the gradient of the curve at that point. Okay, so some basics on rate to start us off. Let's look at the actual sort of experiment where you're monitoring the rate of a reaction continuously. Okay, so as the name, as the title suggests, the method involves following the experiment over the entire duration of the experiment. So you're going to be monitoring the change in concentration over the entire course of your experiment. So this method involves following an experiment over time while measuring the concentration over the duration of the reaction. So we need to have a means of doing that. So it's important that we're able to measure the concentration over the duration of the reaction. So from start all the way to the end, we will be at regular time intervals measuring the concentration or the volume. Okay, so perhaps important to annotate that. So we're doing this at regular time intervals. Okay, so an example, one that you probably have carried out, certainly if you haven't done this very experiment, you would have been introduced to similar experiments, especially at GCSE. If you think about the good old marble chips and hydrochloric acid experiment, where you measure the volume of carbon dioxide produced, or magnesium reacting with hydrochloric acid will produce a gaseous product as well, and you can measure the volume of product being formed over time. Okay, so if we consider this specific reaction, we're starting off with some magnesium, solid magnesium, and we're going to be reacting it with some hydrochloric acid, so aqueous hydrochloric acid. And of course, we're going to be forming the salt, magnesium chloride, which is dissolved in solution, so aqueous magnesium chloride, and we are going to be forming hydrogen gas. Now, how are we going to, what's the most convenient method for monitoring continuously the rate of reaction? What you want to do in this instance is to measure the volume of gas being produced over time. Okay, so we're looking at how much product is being produced over time. And so if we look at our balance equation, and especially look at the state symbols, we can see that there is a change in the number of moles of gas from the reactant side to the product side. So over on the left-hand side, we've got a solid and an aqueous solution. So there's no gas present at the start, but over the course of the reaction on the product side, we're going to be forming some gas. And that gas can be collected, its volume measured accurately. And of course, if it's done at room temperature and pressure, that volume can be immediately translated into the number of moles of gas being produced. Okay, so in this case, the method would be to use a gas syringe to allow us to accurately measure the volume of gas being produced at any given time. Okay, so okay, so the type of reaction where you would use a gas syringe. So, for instance, if Okay, so you need to consider the type of reaction you've got. Is it one that is producing gas? If so, can you very accurately measure the volume of gas being produced? Okay, so that's one way of doing it. You could also collect your gas, in this instance, over water. So bubbling your gas through water into an upturned measuring cylinder that it has been filled with water. Then that gas will displace the water in your measuring cylinder. And again, that allows you to measure the volume of gas being produced. Okay, you can also measure the rate of production of your gas by looking at the mass loss. If you leave your container open so that the gas escapes and you've got that container sitting on the balance, then you can measure in real time how much gas is being produced because of the mass loss due to the gas escaping. And we'll look at that in a little while. Okay, so another important practical thing to consider is what the total volume of gas is going to be in the reaction in question. Okay, so you would need to work out the number of moles of your gas being produced. So moles of must be calculated. So the maximum moles of gas that is going to be produced must be calculated. But of course, that allows you to then know the volume, the maximum volume that would be produced. Okay, so it's important to work out the maximum volume of gas that you're going to produce. Why? Because you want to make sure that the gas syringe you're using is of an appropriate size. So if your experiment is going to be producing 500 centimeters cubed of hydrogen and you're using a gas syringe that only collects a maximum of 100 centimeters cubed, then you're going to run into trouble if you're monitoring over the entire duration of your experiment. Okay, so if you've calculated the volume of gas to be produced in 500 centimeters cubed, then you need to pick a gas syringe that has a much higher capacity or a larger volume. So perhaps a 1 liter or 1 decimeter cube gas syringe. Okay, so we highlight that point there. So knowing that allows you to pick the correct size of Okay, so that allows you to pick the correct volume of gas syringe to use. Okay, so that's the point we've just made here. So if I perhaps link that back to there. Okay, good. So that's an important consideration in choosing your equipment. Okay, so how is the experiment actually set up? Well, what we've got here is a conical flask. And in that conical flask, you've got your hydrochloric acid and you've got your piece of magnesium, and you have calculated that based on the amount of your limiting reactant, typically the magnesium, that you're going to be making a volume that is less than the volume of that gas syringe there. Okay, so that's very crucial. And then once you start your experiment, you would be recording the volume produced at regular intervals, say every 10 seconds. So you've got this graph of volume of hydrogen produced against time, so time on the x-axis, volume on the y-axis, and you can imagine at sort of regular intervals of say every 10 seconds, recording the volume in a table. And what you will obtain is a graph that looks like that. And of course, that graph you would expect to plateau when the reaction is complete, when no more hydrogen gas is being produced because your magnesium has been used up in the reaction. Okay, so a graph showing or looking like we've got here is what you would expect to see. Now, another point to make is that if you are investigating the effect of changing the concentration or amount of one of your reactants on the rate of reaction, then it is important that you keep the concentrations or amounts of all the other reactants constant, and only vary the concentration of the reactant that you are interested in. In that instance, you would need to use a very large excess or very large concentration of the other reactants that you are not interested in, so that over the duration of the experiment, their concentration will barely change. So very negligible change in the concentrations of the reactants you're not interested in. And that means that they are effectively zero order with respect to this reaction. In other words, the change in their concentrations isn't going to affect the rate. So it changes so minimally. So if we have a reaction where you've got A reacting with B to make C, and you want to see how the change in the concentration of A affects the rate of the reaction, then what you would want to do is use a very large excess of B. Okay, so a large concentration of B. So a large concentration of B, which barely changes over the course of the reaction, makes it zero order with respect to with respect to B. Okay, so it is called pseudo zero order because it is only zero order because there is such a large concentration of it with relative to A, the other reactant, which will all be used up, whereas B is hardly used at all. Okay, so not really zero order, but pseudo zero order. So a bit like, or pretending to be zero order, only because there's such a large amount of it. Okay, so a large concentration of B, which barely changes in the course of the reaction, makes it zero order. Okay, so makes it pseudo zero order. So that's another thing to consider when you're doing rates of reactions and monitoring continuously. You want to look at how the rate is being influenced by just one thing, and so you must keep your other reactant sort of essentially constant, or the concentration of that other reactant constant, not changing over the course of a reaction. Okay, so that's a quick introduction to the sort of experiment you would carry out, so monitoring the volume of gas being produced. What other bits of information can be obtained from our concentration time graph, which you would obtain if you're monitoring your experiment or reaction continuously? Well, here is another example of a concentration time graph, and this time round we're looking at the concentration of a reactant and how it changes. So we're looking at the concentration of A and how A is going to change over time and what information that can tell us. Okay, so as we discussed previously, the gradient at any point on that curve gives you the rate at that time over the duration of the reaction. There are other bits of information that we can glean from a curve such as this. And one is the half-life. Okay, so the half-life is the time taken for the concentration of A, in this case, to be reduced by half. Okay, so let's write down that definition. Okay, so the time taken for the concentration of A to halve. Now, if we look at this particular sketch here, we've got our concentration on the vertical axis, got time on the x-axis, and if we're looking for the initial concentration, it's here set at 10, arbitrarily chosen, conveniently chosen. So we start off with 10 moles per decimeter cube of A. Now, half of that concentration is, of course, 5, 10 over 2, right? So 5 moles per decimeter cubed. We're looking for the time taken for the concentration of A to go from 10 to 5. So what you're going to do is draw these dotted lines to the curve and then down to the x-axis where you can read off the time. Okay, so our half-life in this instance from 10 to 5, the t half is equal to 1. Okay, and then we can ask ourselves, right, so what is the time taken for our concentration to halve again from 5 to 2.5 this time? So half of 5 is 2.5. So again, we're going to be looking at 2.5 on the vertical axis, drawing this dotted line to our curve, and then down to our x-axis. And this time round, so we're going from 1 to 2. Okay, so, and again, we find that t half is equal to 1. Okay, so we've gone from 1 minute to 2 minutes. So half-life is 1 again. And then we go, right, what time is it going, well, how long is it going to take to halve our concentration again? So going from 2.5 to 1.25. So we go through the same process again, and we're going to look at halving the concentration, so 1.25 all the way to our curve and then down to our x-axis and reading off time. And again, you can see here that we've got t half being equal to 1. So in this particular reaction where A goes from A to B, the half-life is constant. Okay, so this is peculiar to a first order reaction. Okay, so okay, so the order of the reaction with respect to A must be first order. Okay, so the half-life is independent of our reaction of our reactant concentration in a first order reaction. So that is a very key piece of information here. So whenever you've got a concentration time graph and you measure the half-life of our for our reactant, if this is constant, so there's no change in the half-life as your concentration is halved, then you've got a first order reaction with respect to that reactant. Okay, so very key piece of information. Now, if your half-life is increasing and increasing quite dramatically, then it's very likely you've got a second order reaction. Okay, so you could have another curve, which I could perhaps sketch in a different color. Let's try green. You could have a curve that so maybe looks a bit like that. And again, you could measure, we keep to green, you could measure the time taken for the concentration to halve, which this time round may be, so it looks like 0.3. And then we look at the time taken for it to halve again. This time round, we're looking at about 0. So the new time is possibly about 0.8. So we've got a half-life that has gone from 0.3 to 0.5. And then if we look at the time it takes to halve again, a little bit longer than previously. So the half-life is not constant for the green sketch. I know I could have perhaps made it a bit more obvious, but the point is that if you have a first order reaction, so the sketch in red, then your half-lives will be constant. If you've got anything other than the first order reaction, you're going to get changing half-life. Okay, so something important to note there. So let's perhaps clean up my sketch and let's make it a bit tidier. Right, so we'll leave it at that point there. Right, so what are the alternatives to measuring the gas volume? So we've talked about using the mass loss method, and of course, this is what it would look like. So if we carried out the same reaction, hydrochloric acid and magnesium, and measured the loss of mass as your hydrogen escapes. Now, a big point to make here is that this piece of cotton wool is not present to stop your gas escaping. It's present to stop your hydrochloric acid from spitting out of your flask. Okay, so it stops HCl from okay, so don't be sort of fooled by the presence of a piece of cotton wool, which in no way is going to stop any gases from escaping from that flask. Okay, so it's purely there as a safety measure to stop acid from coming out of your flask as your bubbles of hydrogen burst and rise out of your solution. Okay, so that's very important to note. Another way of monitoring, of continuously monitoring continuously monitoring the rate of a reaction would be to use colorimetry. Now, colorimetry, of course, wouldn't be used to measure. You can't use colorimetry if there isn't a significant change in color from your reactant to product. So, so what you can, so if you've got a reaction, say that is using up. So think about the test for unsaturation where you're using bromine water. Okay? So if you've got a bromine water that's sort of yellow in color, maybe a bit orange in color, and you're monitoring how quickly that bromine gets used up, you could use a colorimeter to measure the absorbance of light of a specific wavelength. So probably my guess would be around about sort of blue perhaps, and that would then tell you in real time and quantitatively how much bromine there is left at any point in that reaction as your bromine water gets decolorized. Okay, so in such an experiment, you would have a graph of absorbance. So got absorbance here on the vertical axis against time, and the absorbance would be an indicator of the concentration of bromine present in your bromine water. So you would be starting off with the maximum absorbance where the bromine concentration is highest, and as the bromine gets used up, you would get a reduction in the concentration, very much like we've seen in that sketch above. Okay, so you could do that. You could also use titrations to monitor the concentration of your reactant at any point over the course of the reaction. So you would, at regular time intervals, take a small sample out of your flask. So it could, in this instance, be a small sample of acid out of this flask, and quickly titrating it against an alkali of known concentration to work out how much acid was present at that point when you took the sample out. Okay, so a number of different methods other than measuring the volume of gas being produced. Okay, so not all sort of universally sort of applicable. So for colorimetry, you need to have a clear, distinct color change that sort of changes. Excuse me. That changes over the course of the duration. So you could have going from brown to colorless, or going from pink to colorless, or blue to colorless, to make that work as well as the other methods. Okay, so at this point, I'm going to stop and see if there are any questions, and then we will continue with our work. So looking at YouTube currently, no questions at the minute, and okay, and if we look at my Zoom chat, There are no questions, so we will continue with our work. Okay, great. So we'll continue our work then. So let's look at a practice exam question, a typical practice exam question on continuous method of monitoring the rate of a reaction. Okay, so this question is from your A-level paper 1 2017, and it looks at the reaction where hydrogen peroxide decomposes to give you water and oxygen. Okay, so we've got hydrogen peroxide here in yellow decomposing to give us oxygen and water. Okay, so it says the student investigates the decomposition of hydrogen peroxide by measuring the volume of oxygen gas produced over time. And then all gas volumes are measured at room temperature and pressure. The student uses 25 centimeters cubed of 2.3 mole per decimeter cubed hydrogen peroxide. Okay, so that allows us to work out how many moles of hydrogen peroxide we've got at the very beginning. Okay, so that's important to note. And from the results, the student determines the concentration of hydrogen peroxide at each time. Okay, so by working out the volume of oxygen being produced, we can work out how many moles of hydrogen peroxide have been used to make that volume of oxygen, and therefore how many moles of hydrogen peroxide were left at that time in the reaction. Okay, so quite a neat sort of intricate experiment to carry out. From the results, the student determines the concentration of hydrogen peroxide at each time. Okay, so in our graph, we've got hydrogen peroxide concentration on the vertical axis. Okay, so all that is with hydrogen peroxide. He then plots a concentration time graph, which is exactly what we've got shown here. Okay, so the first question says to determine the total volume of oxygen measured at room temperature and pressure. Okay, so we're looking at the total volume of oxygen that's going to be made. Need to highlight that at room temperature and pressure that the student should be prepared to collect in this investigation. So how are we going to do that? Well, we need to go back and look at our balance equation here. So our balance equation says 2 moles of hydrogen peroxide are going to decompose to give you 2 moles of water and 1 mole of oxygen. So the molar ratio we're interested in is hydrogen peroxide to oxygen, which is of course 2 to 1. Right, so where do we start? We can start by calculating the number of moles of something. Right? And the only thing we can calculate the number of moles of at this point is hydrogen peroxide. So we know that the concentration is equal to the number of moles over volume in decimeters cubed. Right, don't forget that. So number of moles of H2O2 is going to be equal to the concentration, which we know to be 2.3 moles per decimeters cubed, times the volume, which is given in centimeters cubed, so 25 centimeters cubed divided by 1,000. So that should be 0.025. So we punch that into my calculator, so 2.3 times 0.025, and that gives us 0.0575. Okay, so that's the moles of H2O2. We can use that to work out the number of moles of oxygen. Okay, so number of moles of oxygen so 0.0575 divided by 2 is 0.0288. And then from that, we can use the fact that this reaction is being carried out at room temperature and pressure. So the volume of oxygen is being measured at room temperature and pressure. So we know that at room temperature and pressure. 1 mole equals 24 dm cubed. Therefore, 0.0288 will be equal to 0.0288 times 24. Is 0.69 decimeters cubed. Okay, so that is our volume of oxygen that we would expect to collect, and we're asked to suggest what suggest the operators that would allow this gas volume to be collected, indicating clearly the scale of working. Because if we're going to be making this much oxygen, then we would want to use a 1 dm cubed sort of gas syringe, maybe, if that is that can be sort of obtained, or perhaps a 1 dm cubed measuring cylinder. Okay, so you'd fill that measuring cylinder with water, of course, and then the gas would displace the water. Okay, so that's a good start to the question. If we look at the next part, it says suggest a different experimental method. So we want a different experimental method that would allow the rate of this reaction to be followed over time. So again, we're still looking at the continuous method of monitoring the rate of the reaction. If we're not going to be collecting the gas formed and recording the volume with time, what can we do? Well, we can use the mass loss method. So you can use the mass loss method. So conical flask on your balance and hydrogen peroxide on that into that conical flask. So obviously the starting mass would be, the balance would be turned, so the starting mass would be 0, and then over time you'd see that the reading on the digital balance should go into minus territory as oxygen is produced and leaves the flask. Okay, so that allows you to measure the mass lost due to oxygen leaving the flask. So you can use that. You could also use the titration method. So take a small sample of your hydrogen peroxide at different points and titrate against perhaps iodide, so in a sort of redox titration to work out how much hydrogen peroxide you've got at any point. Okay, so that could be an alternative. And then in the final part of the question, we're asked to determine the initial rate of reaction. So that's one thing we need to look at, the initial rate of the reaction. We also want to look at the order with respect to hydrogen peroxide, and finally the rate constant. So 3 things we need to consider in our question, and doing all 3 exactly as we should sort of net us a total of 6 marks. So let's start with the initial rate of the reaction first. Now, to get the initial rate, we need to go back and consider the curve that we've been given. Okay, so there's our curve. The initial rate is the gradient drawn to the curve at t equals 0. Okay, so we zoom in on our curve, and if I use my ruler function to hopefully allow me to draw a tangent to the curve at that point, I'm going to give it my best shot. Let's see if we can. I suspect I could maybe do a better job. Okay, so yeah, that looks pretty good. I'm going to try and use that tangent to draw to obtain a gradient for the curve at t equals 0. Okay, so what have we got here? We've got oops, I didn't mean to do that. Let's there we go. And if we Okay, so we want to look at the change in y over the change in x. Okay, so we've got 2 points here. There's that point there, and there's that point there. Okay, so gradient is equal to okay, so we're looking at 2 point, I make that to be 2.3, so 2.3 being that point there. So 2.3 minus, we look at this point here, we've got 1. And of course, x to 0 minus, and if we work out what x is down there, so we've got that's 600, that's 700, that's 800. Okay, so we've got 800 there. Okay, so we've got 1.3 over 800. Of course, it's a negative gradient, but that doesn't matter in this case. So 1.3 over 800. Okay, so 1.63 times 10 to the minus 3. Okay, and of course, that would give us, so we've got concentration over time, so that would be units of mole per decimeters cubed per second. Okay, so that is our gradient, that is our initial rate. So back to our the initial rate, we could say C working on graph is equal to 1.63 times 10 to the minus 3 moles per decimeters cubed per second. Okay, so brilliant. The order with respect to hydrogen peroxide. Okay, so how can we work that out? Well, let's go back to our graph. Okay, so if we go back to our graph, we could see if we can work out the half-life of our hydrogen peroxide over the course of this reaction, and if it remains constant or if it changes at all. So if we start with 2.3 and halve that concentration, so 2.3 divided by 2 takes us to 1.15. Okay, so we're looking at 1.15. So here's 1.1. 1.15 is about there. And if we go across to our curve and all the way down. Okay, so we've got T half there to be 900 seconds. Okay, and if we halve 1.15 again to 0.575, so 0.58 we're looking at, so 0.6, so 0.575 will be there. And if we drop down, we're now at 1800 seconds. So the first half-life, T half, is equal to 900. The second half-life, T half, is also equal to 900. Okay, if we just do another one for sort of peace of mind, so divide 0.575 by 2. That takes us to 0.288, so 0.288, so 0.3, 1, 2, 3. Okay, so that's now taking us to 2,700 seconds, and again, T half is equal to 900. Okay, so we've got a constant half-life in this reaction where you've got hydrogen peroxide decomposing. So we can write down that T half is equal to 900 seconds. Again, C graph. And this is constant. Therefore, first order with respect to hydrogen peroxide, or for this reaction, hydrogen peroxide is the only reactant. Okay, so that's the second part taken care of. And then we're asked to calculate the rate constant. So to calculate the rate constant, we need to write down the rate equation. So the rate equation is equal to the rate constant times our hydrogen peroxide, which is of course first order, so it's the power 1. So if we rearrange that to make the rate constant the subject, K is equal to rate over our hydrogen peroxide concentration. And we can then work out using the rate the initial rate we calculated earlier, so 1.63 times 10 to the minus 3 over the concentration for the initial concentration, which is of course 2.3 moles per decimeters cubed, 3, and that should give us a rate constant of 1.63 to the minus 3 divided by 2.3. That should give us 7.09 times 10 to the minus 4. Okay, so rate constant in this case would be, would have units of seconds to the minus 1. Okay, so quite a challenging question, one that you can obtain loads of marks on if you're very systematic in your approach to answering the different parts of the question. Okay, now at this stage, we're almost at the end of our session, and this is very, very quickly going to check that there aren't any questions for me on YouTube, and if not, we will then proceed to sign off. Okay, so no questions at the minute, so over the duration of the session. So as usual, it's been a pleasure to have you join me on this Sunday afternoon. I'm looking at the continuous method for monitoring the rate of the reaction. We've looked at different methods you can use to continuously monitor the reaction. We've looked at some of the data that you can obtain from such a reaction, including the rate of the reaction at any point in time. So drawing tangents to the curve, looking at the initial rate, and also looking at half-lives to work out what order the reaction is with respect to a particular reactant. So do go away and tackle some of these practice problems from your textbook or from past papers. And if there are any questions, please do drop us a line at boostrevision.com. We're more than happy to write back to you with solutions to your problems. Thank you very much for joining me, and hope to see you again next week. Thank you.